Management or Supplier Management. This is going to be the last lecture on Python for a while. Okay, so today we look at some methods that are non-supervised, so we don't need to train them, just like the one before. Next week we will start with a case study. Analysis. I will send you a PDF so that with some instructions, with a book and some instructions, so that you prepare and read, I don't know, 10 pages I think, or 15 pages as a preparation for next week. Okay, but today we are going to be dealing with Python still. So this is a non-supervised method. So this means that no information or knowledge about the dataset is necessary previous to analysis. This is not the case for other methods where you have a supervised method where you need an expert. The principal component analysis basically delivers the directions in space that best explain the variability of data. Okay, and this is what we do. We calculate, or we are going to find out the best directions in the phase space that deliver an explanation of the data, and we are going to quantify this variability. So first we upload a two-dimensional data set. This is done with NumPy, and we do that with I need to import NumPy first. MP, so numerical Python, and also the matplotlib for the graphical description. But this is just standard. Okay, so we create a data set which is basically going to be created with a random function, np dot and then rng rand. Okay, rng is a random state from that we have just defined. It should have dimensions 2 by 2, so 2 dimensions, and it should have 200 points. It should be transposed, and we now plot it. Scatter x double point comma 0 x double point comma 1 and then we just plot the axis, let's say equal. If we plot it, it is going to give Mistake, why? Okay, I had a bug. Anyway, we just we create with this code, we create a data set. We can take the last line off. It's just I don't think it helps. So you see we have 200 points distributed along two axes. The axes are distributed equally, okay, and the thing is that, let's say you can say the x-axis is one KPI of yours and the y-axis is another KPI, but you can see that the information is ordered so that we have a special direction in the diagonal, okay? As you see in the diagonal from top right to left bottom, all the data are organized neatly. So it is expected that this diagonal is important for the data set. Okay, so we are going to try to quantify the variability along this diagonal. In order to do so, we create a sklearn decomposition. Sklearn. I guess I need to import sklearn first. Import PCA, and then PCA is PCA with components equals to 2. So 2 components, and then I say PCA dot fit of x. Okay. So this performs the principal component analysis, and I can print them. Print PCA components underscore, and you see these two vectors are the directions, one in the direction of the points and one perpendicular. Okay, I can visualize this in an easy way, but this line of code is not relevant for the exam. Okay, so I put it here. This line of code not relevant for the exam. So whenever I put that, it's just for explanation purposes, so you don't need to, let's say, go into detail with that. As you can see, okay, this is just the same data set as before, but I have visualized with this code two arrows. One wide arrow going in the long direction, longitudinal direction of the data set, and one arrow going perpendicular to that. Okay, so it turns out that the length of the arrow is giving you the amount of explained variability or explained variance in our model. So if I say PCA print explained variance, he will tell me that with the first component, also with the first direction, I can explain 65 sorry, 76.25% of the variability of the process, which is a lot, with just one direction. And with the second component, I can explain 1.8% of the variability of the process. Okay. This is represented graphically with the length of the arrows. You see the one arrow going along the direction of the data is longer than the one going in perpendicular. Okay. So this method is very, very powerful. So I just represented this thing in 2 dimensions. But if you have, let's say, a KPI management system with many KPIs, which you will have this describing the quality, the supplier processes, and so on. We will see that in the case study. A management system with many KPIs, and you want to know what are the most important KPIs and what are the most important sources of variability, you go and use PCA accordingly. Okay, and then the PCA will automatically, without any previous knowledge, so you don't need to think or know anything about it, without any previous knowledge, will tell you what are the most important directions in the explanation of variability. Okay, so this just as a very easy first example. What happens if we have more than one direction or one dimension, or more than 2 dimensions? Well, we can also use PCA, but we need to do something before. Okay, we need to explain right away what we need to do is we need to scale the data set. Okay, let me please first load the packages as we always do, and load the data set. For that, we get dataset from breast cancer. Okay. So in this dataset, we are going to represent a data frame with data from the women that have had breast cancer. So, and we represent with this, we represent the radius of the cancer, the texture, the mean texture, the perimeter, the area, the smoothness, compactness, concavity. All these things help us understand the nature of the cancer. So now imagine you're a doctor and you have 30 different variables, to decide what if your patient is sick seriously or not. And you need to decide on a certain treatment. Depending on your decision, the life of the patient is going to be at stake. This is just one example, okay, because we have this data, but imagine you have 30 different customers, okay, and you need to decide what is your most important customer, who is giving you more variability. okay, and so on and so forth. So this is a method to treat. This is impossible. It's impossible to do this, or it's, yeah, I don't know. I cannot do it if I do it with my hands, okay, just with a piece of paper. But with the help of our friend Python, we can analyze this and know very well what is or what are the most important sources of variability in our data set, and make the correct decision. Okay, so the first thing we do is we scale the data set before processing. Okay, so we scale the data as we have done in the past. This is just a normalization, okay, as we have done in the past in statistics, for instance. Pre-processing, import standard scalar, when scalar equals standard scalar, okay, and then we say scalar dot fit of what? Of the data frame df. And then we say scaled data equals scalar dot transform data frame. And then we say scaled data dot head scalar is not defined. Yes, I didn't write it correctly. I need to write scalar. Scale data. Yeah, I cannot put it like this. It's because it's an NumPy array. So as you see, now we have rescaled our data. So each column, we had the mean radius here. This is the mean radius. It's not anymore between with this value 1799, but it's now 1.01. Okay. What we have done here is we have created the standard scalar. We create a data set with the same statistical properties, but normalized between with a normal distribution with mean equal 1 and standard deviation equals 0. Okay, so this is a normalization, just as we have done, as I said, in statistic. Is the so-called Z transform, if you recall that from statistics. Okay. So, and now how do we know what are the most important sources of variability? Well, we perform a PCA analysis, which is called PCA, number of components. We say 2 also, so we're going to reduce from 30 dimensions to 2. And we're going to know how much variability we are explaining. Okay. We perform a PCA. On the scale data, and it gives a mistake. Why? Number of components 2, it's wrong. yeah, I need to say equal to. Okay, so now I have a new a transform data set which has 569 data, but only 2 columns. And now we are going to represent this graphically. So graphic representation. Okay. Fixed size equals 86. I know I can let's keep it simple. So we have scatter the PCA, the first column, then XPCA, the second column, and then C, the color is going to be cancer target. Okay, so this is our important value, and the CMAP is going to be I don't know, autumn, just like yesterday. Okay, and we can say PLT X label, the label of the horizontal axis is first principal component, and the PLT Y label is second principal component. If I press Shift Enter, you will see that now we get the information represented in only 2 dimensions. Okay, I can say, please print me the PCA components, and he will print me the PCA components. I can also say, just as we did before, print me the PCA explained variance. So how much variability? This is a typical question that your boss asks you. So okay, this is very good. This is you are explaining now me what are the most important areas, but how much variability are you explaining with this? Okay, so you can explain 18% of the variance with this concept. Okay. With just we are bringing from 30 to 2 variables. Okay. We can also explain the variability in a so-called heat map. Okay. So we are asking the question, how much variability is explained by each KPI. Okay, and this is something that is going to be very important for you in the future, because you want to know how much variability your let's say one customer is giving you. PCA components, columns equals cancer, future names, plt.figure, no, I do it SNS, heat map, and then df.components. Okay, so you see here, what do you see here? Okay, you see here in the horizontal axis, you see the, let me put it a little bit more, a little wider so that we see everything. Okay, so now we see, what do we see? In the In the horizontal axis, you see mean radius, mean texture, mean perimeter, mean area. Okay, these are the KPIs that we have in each column. Okay, so the KPIs. And then 0 is the first component, the first principal component. 1 is the second component. And the color is telling us, the heat map, how much variability it's being explained by each KPI, by each principal component on each KPI. Okay? So you see the mean radius is being explained with this color, so around 0.2 positive on the first principal component and minus 0.2, so 20%, around 20% of the variability, and so on. Okay, this is something that in no way you can do in no way you can do with Excel or something similar. Okay. So now something maybe that you find interesting, because your phones work like this. Okay. They use a combination of support vector machines and PCAs to detect your face. Okay, so now we do some face recognition with PCA. Okay, we are going to load the dataset from sklearn.datasets, import fetch LFV people, and then we're going to get some faces from some political guys. Fetch LFV people, mean faces per person equals 30, so I get 30 images per person. There are I think 5 different political guys, so I get a data set with 2,370 times 2,914 dimensions. Okay, so those are images. I can plot some data, okay, so that we see what we're talking about. And this is not, let's say, not relevant for exam, this code. So I print some data. Okay, so you see here Madeleine Albright, you see Schwarzenegger, you see George Bush, and all these guys. Okay, and we want to our system to be able to recognize the a new data set, so that we can explain the variability of our data set, and we can recognize faces with our PCA, the principal component. So now we perform a PCA on this very multidimensional data set. We need to do it as a randomized PCA, and our model equals randomized PCA with 100 as parameter of the faces data. and we print the number of components in the dataset based on the variance explained. So you see, if we take 100 components, we can explain 90% of the images. If we only take 20 components, we can explain 75% of the images, as in the plot. Okay? And what this tells us is that our data set, we can explain with, let's say, 100 components, we can explain 90% of all our pictures. Okay? So only with 100 characteristics we can recognize these people. And this is what your telephones are doing when you first log into your phone, and it asks you to move your face to the left, to the right, up and down. What it's doing is learning this 100 features, components, so that it can recognize you from different perspectives without having to learn all the details in your face. Okay? So another interesting algorithm is the, let me wait a second. Yeah, it's called TSNA. Okay, TSNE algorithm. It means T distributed stochastic neighbor embedding algorithm. Okay. This is again a non-supervised method. And this is the last thing we see today. It's a non-linear technique that explores data sets and enables a visualization of multi-dimensional data. Okay, the difference with PCA is that PCA is a linear dimensional reduction method. It just takes distances in an Euclidean space, and PCA tries to maximize the variance by keeping the distance between the data constant. On the other side, on the other hand, TSNE is a non-linear method that only keeps the distance between the points or local similarities. Okay. The algorithm calculates the distance between data in the high dimensional space and projects this into the lower dimensional state, two-dimensional, in order to visualize it. Trying to keep the relative distances by optimizing a cost function. Okay? So let's implement it. First, we find the similarities between the points in the high dimensional data or the state. Excuse me, between the points by implementing a t-student distribution. Okay, the reason why we use a t-student distribution is because it has only one liberty degree. This is the first step. Then the second step, we do an example later, is to calculate the distance between the points of the high dimensional space and project them into the lower dimensional state. So I go import matplotlib.pyplot as plt as before, import seaborn as sns, sns.set, import numpy as np. Okay, this is just standard from sklearn.data sets import load digits. Digits are equal load digits and digits dot data dot shape. We can plot some data, okay? So that we know not relevant for exam. So we plot some data so that we know what we're talking about. For here I need to go in and I am set. Okay, and now it's expecting some in and here also and here also. Good. So here we're plotting some data. Okay, so these are just numbers that you see. And our data has, so each picture has 8 by 8 dimensions. Okay, so 64 dimensions. And we have a total of 1797 images. So we have a vector of digits target. Okay, so we know we have 10 numbers. So target no things. So we know we are having from 0 to 9. Okay. And we only are going to use 600 of these images, so that it's not so much. And now we tell him to import from sklearn.manifold import tsne. Okay. Now we tell him how many components are we going to represent. They're going to be 2. Number of components equals 2. Random state equals 0. And then I tell him to transform the data x, okay, just the 6 number, and create a tsne object. We can represent this object. Okay, we can print the object by importing pandas SPD and then describing our data frame. Yes, in EDF. Wait, I need to insert some code. So this goes in. And this goes also in. So you see, I get the object represented, and now I can represent the scatter plot with SNS and give a representation of 2 dimensions of our 64-dimensional times 64-dimensional space. Okay, so now I print here, and now you see what is very interesting, and this result is super powerful. Okay, so what you see here is a representation of 600 images. Okay, in not in 64 by 64 pixels. Okay, so each image is 1 point, but all the images that are similar are put together. Okay, so all the zeros are this violet are put together, and all the greens, dark greens, are the 6 are put together. It has problems representing the 1s because they are similar to the 7s, okay, and similar to the 2s. So that's why the points of the 1s are scattered, the reds, and so on, okay? So you see here all the points, all the palette I'm using. Just prepare that for you. So now imagine following situation. You have 64 different KPIs in a data set, each coming from one car. All the BMWs that are driving around Germany. Okay, so one is the age of the driver, other is the consumption, other is the street, the road, the position, the, I don't know, the oil consumption, everything. It's been sent to the cloud nowadays. With this simple method, TSNA, you can give your managers in one image. So in one image, you can give your managers a representation of the world they are navigating. So you can represent all the customers, the 64 by 64, 64 dimensions, whatever you want. It really chunks dimensions until thousands, okay? You can represent this information in one image, which gives your marketing department and your logistics department and so on a very accurate image of how scattered their different products are. You see here, if you picture the zeros as one product, you can see here that they behave similarly, and that you can have a strategy for the zeros, you can have a strategy for the sixes, but if you put a strategy together for the ones, you will have problems. Okay, so this TSNA is a super important strategic method to represent information in a managerial manner. Okay. Questions, please. Questions, please. Is anybody online? Hello? You're cool? So do you have any questions, Anna or Christian? Katerina? Or are you lost completely? And I need to start again? Well, no questions. No pain, no gain. Okay, well then, I guess that's it. I will send you a PDF with the information, of course, with the lecture, but also with a book that you please read until page 17. Okay, I will put that in the mail together. Please read until page 17 of the PDF I'm sending as a preparation for next week's lecture. Okay, page 17, 17. You need to study a little bit and prepare for that. Okay. Well, great.